welcome to module number 19. This is our short week. So we only have 2 modules for this week, and we're going to continue on with our calculations of equilibrium. So today it's not too much work. We're going to go through page 25 and 26. I'm going to set you up for how to do something called an ICE table. And then on Friday's module, it'll be working through sheets on your own to see if you can do those calculations. Okay, so for this one, it's really just one equilibrium equation about hydrogen iodide gas breaking down into hydrogen gas and iodine gas. So you can see the equation written right here for question part A. And then this is the same equation that takes you on to page 26. Okay, so it's one equation. We're going to summarize all of equilibrium again on page 25. And on page 26, I'm going to show you the next part of the calculation. It's then how to take the K value, which we know is the equilibrium constant, and then how do you figure out what the concentrations of the gases would be at equilibrium. Let's say you're given a certain volume and a certain molar concentration of one of these gases. Let's figure out what the equilibrium concentrations would be. And that would be something that you would actually, you could figure out in the lab to be able to use that for industry or something like that. Okay, so here we go. So there's our balanced chemical equation. And if we started off with a colorless gas and we end up with that iodine gas, don't forget that's the one that's dark purple, how do you know that equilibrium would be reached? Well, don't forget, it's those macroscopic observations that are going to be constant at equilibrium. So if you start off with colorless gas and you get to something violet, it's going to be light purple. If you started the other way, if you started with something that's completely all dark, if you had only iodine and hydrogen gas, at equilibrium, it's going to be producing some gas that's colorless. So no matter which way you start this equilibrium, once it reaches equilibrium, where the rate of the forward equals the rate of the reverse, the concentrations are going to be constant, and so the macroscopic properties are also going to be constant. So it's going to be light violet. Very good. What does it mean? Of course, it means that the rate of the forward is equal to the rate of the reverse, and you can talk about breaking of the bonds. That would make sense. Okay, so here we go. If you're given the Ke value, so that's your equilibrium constant at a particular temperature, remember that temperature can affect equilibrium. So let's say our K value is 0.25. Write your expression for what that K value is. Remember, it's the concentration of the products over the concentration of the reactants. Assuming that we're dealing with all gases here, so they're all going to be involved. And then don't forget, because it was a 2-to-1 ratio, you need to make sure you've got your hydrogen iodide concentration squared. Okay, now what does it mean? Remember, what does that K value mean? If it's less than 1, if it's equal to 1, or if it's greater than 1, it just tells you a little bit about the concentrations at equilibrium. So in this case, if our equilibrium constant is less than 1, it simply just means that the concentrations of the reactants are going to be a bigger number, because you're going to have a bigger number on the denominator part of the equilibrium expression. That's all that it means. But remember, that's the terminology that we use with equilibrium. Does the reaction favor the reactants or the products? And so we're just going to say for this one, well, clearly it's going to favor the reactants, because K is less than 1. Okay, can I get you just to ignore this third part here? That's all of this part that is kind of complicated, and the take-home message is just that when you're calculating the K, so K equilibrium, you have to be able to calculate it using the lowest whole number ratios. If you don't use whole numbers, like over in this case over here, if you use halves and halves, it doesn't work out to the same thing. So K is very dependent upon the fact that we're using whole number ratios for all of our concentrations in our balanced chemical equation. Okay? Ignore the rest if it looks complicated. Don't worry about that part. All right, here's where we're going to summarize everything. So again, I don't want to scroll back up and down to where the equation is, but you can I'll just refer to it, and then I think you get the idea of which way the shift is going to take place. Okay, so let's see, we've got a system change. What if we decrease the concentration of the iodine gas? That's my stress. Which way is that going to shift? If you decrease it, it's going to shift towards the products to the right. What's the effect on the K going to be? there is going to be no change to the K value. No change. Why? Because the concentration of my HI is going to go down. The concentration of the H2 is going to go up. The concentration of the I2 is going to go up until a new equilibrium is established. And then mathematically, if you were to put those concentrations in, you're going to get the exact same value for K. K does not vary because, again, you've just established a new equilibrium. Does that make sense? Okay. Remember, any stress is going to cause a shift, and then a new equilibrium will be established. And when that shift takes place, there's only one thing that's going to change the K value, and that's the one at the bottom of this table. That is the temperature. Okay? So, I mean, you could put some fake numbers in and see how it works, but that's kind of what we're headed to. We're going to look at this thing called an ice table. So we're going to get to that point and you can see mathematically how it works. Okay, next one. What if you added some hydrogen iodide gas? Well, that stress is your increased concentration of your hydrogen iodide gas. Which way is it going to shift? It's going to shift it to the right. Is that going to vary or change the KEQ, the equilibrium constant? No, because the only thing that's going to change the equilibrium constant is going to be a change in temperature. Next one, if you decrease the volume of the vessel, remember these are all gases. So if you're decreasing the volume, you are increasing the pressure. So now you need to look at the ratio of the molecules. You've got 2 on the reactant side and 1 + 1, 2 on the product side. No shift is going to take place. Also, no change to the equilibrium constant. What if you add a catalyst? How does that affect equilibrium? Well, it affects the forward in the same way it affects the reverse. All it does is means it's going to reach equilibrium faster. Okay, so no shift, no change to the KEQ. The little triangle means change, right, delta? Okay, cooling down the equilibrium. We know in this case that cooling it down, so that's a decrease in temperature. Now you need to look to see where the heat is. Is it on the reactant side or the product side? It's on the reactant side. So if you decrease the temperature, it's going to be shifting your equilibrium to the left. Does that make sense from the practice questions that you've done? And will it change the K value? Yes. You will get an increase in the hydrogen iodide concentration. You'll get a decrease in the hydrogen gas concentration. You'll get a decrease in the iodine gas concentration, and you will get a decrease overall in the K the equilibrium constant for this equation. Okay, so that's a good review on equilibrium. Now let's move into the second part of the lesson where it's figuring out what the actual concentrations of these gases could be. Okay, here we go. I've just written the expression down again. There's our equilibrium expression. That's from the previous page. Okay, same equation. Let's see if we can figure this out. So you're going to set up something called an ice table. Okay, I stands for initial concentration. C, what's the change in concentration? E, what's the equilibrium concentration? We need to make something something in this box, in these boxes, be a value of X. Then we're going to solve it, because what we're going to do is we're going to set up the equilibrium expression right there, which we did on the previous page, because we know the K value is 0.25. So can you see here in this table how I've set that up? Does that make sense? That if that is the equilibrium constant, then we can figure out this concentration, and this concentration, which are going to be the concentration of the gases at equilibrium. Okay, so we're going to use that expression, and we're going to use this little table setup, and we're going to see if we can make this make sense. Okay. Start off. What is the initial concentration? Well, it's telling us up in the question that we have 0.15 moles in 5 liters of HI. So we are starting off with an initial concentration of that colorless gas. And what is that concentration? You want to do that math quickly? that would go in this box right here. 0.15 divided by 5.0, and I know that my initial concentration is 0.030 moles per liter. Okay, does that make sense? What is my initial concentration of the H2 gas and the I2 gas? 0. I don't start with anything in there. Therefore, can you see what's going to happen at equilibrium? When it reaches equilibrium, the concentration of the HI gas is going to go down. The concentration of the H2 and the I2 are going to go up. By what factor do they go down and up? You're going to use the molar ratios to help us figure that out, okay? So what we're going to do is, let's say this is our value for X. Does it matter what I solve for X? Well, my X value has to be something. It could be anything. I could let X be the equilibrium concentration of the H2 gas. I could let X be the concentration of the HI gas, the change in concentration. I could let X be the equilibrium concentration of the HI. Mathematically, you want to set this up to be the easiest problem you have to solve, because on the next page, the next couple modules, we're going to get into using the quadratic formula. So let's make it easy and make it the easiest way. What's the easiest thing we can do so that these values, which are going to be right here, here, and here, are the ones that I'm putting into my equilibrium constant and solving for. Okay, so what have I let X be? I've let X be my H2 concentration at equilibrium. Okay, this is also going to be X. Why? Because they're both going to go up by a factor of 1x. Okay, have a look at this. I'm going to fill in the rest of the table, and then I'm going to put it into the equilibrium expression. But does this make sense? That I know my concentration to begin with is only 0.030 moles per liter of the hydrogen iodide gas. Clearly, this concentration is going to decrease by a factor of 2x. Where does that 2 come from? Let me change the color so you can see it. 2. Okay, this is a 1 and this is a 1 ratio here and here, aren't they? This is going to go up by a factor of x. This is going to go up by a factor of x. And so at equilibrium, the concentration of my hydrogen iodide gas is going to be 0.030 take away 2x. Now, take a minute, see if that makes sense to you. Okay, this is the hardest part, figuring out what you put into an ICE table. The Bozeman science video that I posted on the last module, he gets into talking about ICE tables. Okay, this is the setup and this is how you solve for it. So what are we doing? We want to figure out what X is, because if I can figure out what X is, I can simply plug that number back in and get an actual concentration. And look at the math. It's not going to be too tricky, is it? So I set up my equilibrium expression. I've got my concentration of the products over my concentration of the reactants, and I've got the coefficients as the squares or the 3, whatever it happens to be. My coefficients are used as my exponents. So x times x will be x squared. 0.030 minus 2x will give me to the square. Once you get to here, okay, once you get to this point here where you've got a square on the top and a square on the bottom, do you know what you have to do? If you square root both sides, you're going to get rid of those exponents. That's a math rule. Do you remember that rule? Okay, so once you get down to here, then I think you're good to go. 0.5 equals x over bracket 0.030 minus 2x. Now it's just solve like you would in any algebraic formula. Solve for x. Once you get down to the end, you have now a value for x, and in this case, in this equation, our x value is equal to 0.0075. That, because x was the concentration of the hydrogen gas and the iodide gas at equilibrium, I can simply conclude that my hydrogen gas equilibrium concentration and iodine gas equilibrium concentration is equal to 0.0075 moles per liter. And if I want to figure out the hydrogen iodide concentration, I now plug it back into the equation, 0.030 minus 2, put in your X value, and the concentration of the hydrogen iodide, is 0.015 moles per liter. And that's how you use the equilibrium constant. You have to be given it in the question, okay? I have to be given something initially so I know where I'm starting from. And you're gonna make one thing X, make it the easiest thing possible, and then solve for X, okay? Down below here, it shows you what if you chose something else to solve for X. And that's really tricky, right? What happens? Sure, what if I decided to make this value X? You watch this, right? Okay, this one's not so bad, 0.030 take away X. But if that's for 2HI and I make the change X, then what's this one gonna have to be? Well, then it's gonna be plus 0.5X. So at equilibrium, it'll be 0.5X. Same thing over here. And then look at these values. Imagine taking these values and popping them into the equilibrium expression. That math's too hard for us to do. Would you get the same answer? Yes. But why do that, right? Why do that? Look at the bottom one. Can you see here too? What if we made this value X? Great. Well, then you've got this time a half X and a half X. Boy, boy. Very cumbersome, avoid if possible. All right, so this lesson is just done now. We're finished with looking at an initial value of an ICE table, and then in the next module this week, we're gonna look at doing these calculations, and maybe we'll have to do the quadratic formula for one or two of them. Okay, thanks. Good luck, guys.